Good day everyone, my name is Ayan Crudat Cumia and now I will present the study entitled Engineering Geological Analysis of Municipal Solid Waste Landfill Stability. Municipal solid waste is produced in massive quantities as a result of rapid urbanization and an active lifestyle. Municipal solid waste is currently treated and disposed using three main methods: composting, incineration, and landfills. Landfills are due to the numerous technical properties of municipal solid waste. Landfills are susceptible to instability when outside influences are present. Analysis of slope stability is critical issue for effective landfill operation. Seismic effects of municipal solid waste landfills have been widely studied and investigated in recent years. Various techniques and models are applied to describe the municipal solid waste characteristics under seismic conditions, including the dynamic stability of newly constructed and extended landfills. Landfill instability has been the subject of numerous recorded occurrences in recent years. The landfill failures can be separated into two categories: uncontrolled or open landfills and engineering or sanitary landfills. Flow slides in the MSW body slips along the layers or the foundation, and failures like rocking in the cover layers or the MSW body are examples of failures in engineered or sanitary landfills. From an engineering geology viewpoint, landfills can be regarded as artificial geological bodies composed of municipal solid waste with macroscopic structural planes between the waste materials. The artificial geological body has a special structure and occurs in a certain geological environment. There are similarities and differences between a waste body and a body of natural soil or rock mass. For example, both the artificial and natural bodies are influenced by changes in the geological environment. However, the interaction between the waste body and the geological environment will be more sensitive than that of natural geological bodies because of the heterogeneous nature of the municipal solid waste and because the properties of the waste material vary with the time. The geologic body or internal factors and the geo-environment or external factors can be used to discuss the determinants of landfill stability, the engineering characteristics of the municipal solid waste on a mesoscale, and the waste body's structural features on a macro scale are two perspectives from which to examine the internal causes. Furthermore, the impact of outside variables such dynamic engineering geological processes is also examined in Figure 1. The composition and structure of municipal solid waste. Its composition is more complicated than that of natural soil. It usually includes food waste, paper products, textiles, plastics, rubber, ash, and so on. Most organic matter can be decomposed by microorganisms, and some inorganic matter can be chemically decomposed. However, most inorganic matter cannot be decomposed or decomposes very slowly. The composition and the proportion of the municipal solid waste components in the waste body will vary with time, leading to significant differences in their engineering properties. The time-dependent properties of municipal solid waste must be considered when discussing the engineering properties of waste. During the initial stages of decomposition, the municipal solid waste properties are different from those of soil because a large part of municipal solid waste consists of organic waste and some inorganic matter. As the decomposition process proceeds, the proportion of soil granular medium increases. Some of the reinforced paste loses its reinforcing effect and the municipal solid waste acquires the properties of soil. The physical properties of municipal solid waste. The unit weight, moisture, content, porosity, hydraulic conductivity, and total waste capacity are among MSW's physical characteristics. The geotechnical qualities of municipal solid waste are mostly influenced by its physical attributes. Shear strength of municipal solid waste. Evaluating the shear strength of municipal solid waste is a crucial aspect of landfill studies, especially when it comes to static and seismic slope stability evaluations. Shear stress can be estimated using a variety of techniques, including a load test, laboratory testing, field testing, and back analysis of field case histories. Next is the structural features of the waste body. The structure control theory, which holds that the behavior of a rock mass is governed by its structural geological features. It is used in engineering geology to characterize soil or rock mass. The macroscopic structural planes of the landfill body are the interim cover soil, the partial soil foundation, and the landfill's bottom liners. Landfills exhibit different top-down characteristics due to the varying ages of the materials within the waste body, the impact of the degree of deterioration, and the presence of intermediate covering soil layers. Then, the structural planes in a landfill body. The behavior of the planes governs the strength and deformation behavior of a geological mass with a layered structure. Layered geological bodies are prone to deformation and sliding along the bedding. This is the conceptual framework that describes the physical and chemical characteristics of landfill garbage, and the surrounding geological environment is known as the geological model of a landfill body. Leachate production, pollutant transport, and the long-term environmental effects of landfills are all commonly understood using this model. The bottom liners and a portion of the foundation soil, the interim cover soil, the top cover layer, and the interface surfaces of the landfill expansions are examples of structural planes in landfill bodies. The municipal solid waste is supported by liner systems, which are utilized to stop subterranean water penetration and restrict and regulate the flow of polluted fluid. Liner systems therefore shield groundwater and soil from contaminants that come from the waste. By regulating the material flow between the landfill body and the natural geological mass beneath it. The bottom liners serve as the barriers that prevent seepage and fouling. Compacted clay or silty clay often makes up the top cover layer and the interim cover soil. Clayey materials are utilized as landfill cover layers and provide geological barriers in the waste mass. They are made up of minute particles. It have complicated porous structure and have a very low permeability. Nevertheless, there is very little interface shear strength between the cover layer, which is made up of clayey materials, and the liner system, which is made up of geotechnical composite. These interfaces serve as a weak structural surface which increases the instability of the landfill body. The liner system often acts as a potential sliding surface, and failure can occur as resulting of sliding along multiple interfaces within the landfill liner system. Then last in structural features of waste body is leachate and landfill gas. Leachate comes from the liquid in the waste and it is enhanced by water infiltration and rainfall. Heavy metals, inorganic macrocomponents, dissolved organic debris, and xenobiotic organic compounds are among the contaminants found in landfill leachate. The influence of leachate on the stability of the waste mass and showed that leachate within the waste mass has a negative effect on the stability. The decrease in stability is in approximate accordance with increased leachate yield. Landfill gas is generated within the landfills by decomposition reactions, including anaerobic biodegradation of the organic waste content and chemical decomposition of some inorganic matter in the municipal solid waste. The landfill gas consists of methane, carbon dioxide, oxygen, and non-methane organic compounds. The production rate of landfill gas is proportional to the organic matter content and is modeled as an exponentially decreasing function of time. The generation and migration of landfill leachate and gas have a negative effect on landfill slope stability. In sanitary landfills, the amount of leachate and landfill gas can be limited and recycled by a landfill collection and removal system. However, in open landfills, leachate and gas collection and removal systems are rarely available. With the high pore pressure caused by liquid and gas pressure, the effective stress of the municipal solid waste material decreases, leading to a decrease in shear strength of the landfill body. Landfill failure occurs when the shear strength is reduced beyond a certain threshold. Noted that excess pore pressure caused by the silting of landfill gas, which could not escape because of the high levels of saturation in the waste. It played a significant role in the Payatas landfill failure. And in external factors is the effect of dynamic engineering geological processes. An artificial geologic body influenced by dynamic engineering geological processes is what is commonly referred as landfill body. These processes include engineering geological processes brought on by human activity as well as natural cycle geological processes that impact and jeopardize engineering endeavors. There are two types of psychogeological processes. First one is the endogenic and the second one is the exogenic. In endogenic processes, earthquake and volcanism are examples of endogenic processes that are brought on by internal earthly forces. There are several ways in which earthquake can significantly impair the stability of landfills. Permanent displacement brought on by an earthquake could harm the internal pipe or network utilized for leachate collection or circulation. Then, the exogenic processes, the forces on or above the Earth's surface are the source of rainfall exogenic processes. Rainfall and water corrosion are the main factors affecting landfill bodies. The most frequent cause of geological body failure is the rainfall. Then last is the human engineering activities, leachate recirculation, to excavation, and overload. In a bioreactor system, leachate recirculation is used in some sanitary landfills. Apart from energy production and easier leachate management, landfill bioreactor technology offers many benefits including faster subsidence, higher stabilization rates, and quicker decomposition of trash. Leachate evaporation and leachate absorbance by the waste body can reduce the overall volume of leachate during recirculation. Based on the landfill failure cases reviewed in this paper and on engineering geological analysis on municipal solid waste landfill stability, some suggestions for landfill operation are presented. The study of modern landfill stability should concentrate on the weak foundation soils and the geosynthetic interfaces rather than the municipal solid waste, because so many landfills fail due to sliding over many interfaces inside the landfill liner system and weak subsoil. Certain steps can be taken to avoid failures like adopting geosynthetic materials with rough surfaces and improving the foundation's design. And that's all for the presentation of engineering geological analysis of municipal solid waste landfill stability. Thank you.